ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ವಿಪುಲ ಬುದ್ಧಿಯನಿತ್ತು ಸಲಹು ವಿಮಲೆ ವಿದ್ಯಾಭಿಮಾನಿಯೇ ವಿಶ್ವವಿದ್ಯಲೆ ವೀಣಾ ಪುಸ್ತಕಧಾರಿ ದೇವಿ ಶಾರದೆ ನಮಿಪೆ ನಿನ್ನನು ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ಪರಮ ವಿದ್ಯೆಯ ಪೋಷಿಸಿ ಪಾಲಿಸೆನ್ನನು ಪಾವನಿಯೇ ದೇವಿ ಶಾರದೆ ನಮಿಪೆ ನಿನ್ನನು ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ವಿಪುಲ ಬುದ್ಧಿಯನಿತ್ತು ಸಲಹು ವಿಮಲೆ ವಿದ್ಯಾಭಿಮಾನಿಯೇ ವಿಶ್ವವಿದ್ಯಲೆ ವೀಣಾ ಪುಸ್ತಕಧಾರಿಣಿ ವಾಗೇಶ್ವರಿ ದೇವಿ ಶಾರದೆ ನಮಿಪೆ ನಿನ್ನನು ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ಹರಸು ಎನ್ನನು ಹಂಸವಾಹಿನಿ ಹರಿಗೆ ಹಿರಿಯ ಸೊಸೆಯುನಿ ಗರ್ವ ನೀಗಿಸಿ ಗುರುವ ಭಕ್ತಿಯ ನೀಡೆ ಗಾನ ವಿಶಾರದೆ ದೇವಿ ಶಾರದೆ ನಮಿಪೆ ನಿನ್ನನು ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ನಿನ್ನ ಅನುಗ್ರಹ ಪಡೆದ ಮನುಜನು ಜ್ಞಾನಿಯಾಗುವ ಜಗದೊಳು ಸರ್ವೋತ್ತಮ ಜಯ ರಾಮ ವಿಠಲನ ನೆನೆವ ಜ್ಞಾನವ ಕರುಣಿಸು ದೇವಿ ಶಾರದೆ ನಮಿಪೆ ನಿನ್ನನು ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ ವಾಣಿ ಬ್ರಹ್ಮನ ರಾಣಿಯೇ
Okay. Yes, sir. Sanjay, sir, we can start.
Yeah, let's start actually. Is Rishit
Okay,
there?
sir. Okay.
I'm actually on mobile. I'm just traveling home. But yeah. So hi Rishit, welcome here. Really nice to have you here. Uh, yeah. So we're just having a
Vedant,
quick
shall I
little
start?
break here. Yeah, please start.
Yes,
Please
please
start.
start.
Good evening, all, and welcome you here for Skill Development Program with Mr. Rishit Davli. Firstly, I would like to welcome Mr. Rishit Davli, who is the high school student and is a TEDx speaker. To share his knowledge with everyone, he mentors at TensorFlow User Group Mumbai and organizes group Global AI Mumbai and Kotlin Mumbai, and is an international speaker. He is also an AIML moderator and member of Google's Community Leads platform. He is also a Google AI Explore ML facilitator and certified TensorFlow developer. He is also interested in research and has published multiple research papers in the field of AI and mathematics. He has also represented the country in various hackathon and competition and even won a few while representing the country. We all are awaited for you to start AIML and data science session.
Thank you for the beautiful introduction, and um, it's my pleasure to be here. Thanks for inviting me here. Thanks for the beautiful introduction. So, hi everyone, I'm Rishit. You maybe know a bit about me by now. Thanks for the beautiful introduction again. And so I'll not go in detail with this slide since a lot of this was already covered. Uh, So just I'll say that if you want to know more about me, my coordinates are at rishit.tech. You can know more about me at this website. So today we'll be talking all about machine learning, as you might have seen from the title. But what we'll not only be doing today is not just discuss machine learning from a theory perspective. So I'll maybe give you a long boring lecture about machine learning. That's not going to happen today. So what we'll be doing is we'll understand some concepts of machine learning from the very big from a beginner's perspective, and then you'll go ahead and build something together. So we'll build something together in this talk, and you'll also be able to reproduce that by your own. So yeah, that will be the idea of this talk. We'll first go ahead with some basic concepts, and then we'll try and build something with the concepts we have learned. So a bit about what we'll be building at the end of this talk. So we'll be building a simple classifier, so which given an image can tell you if it's an image of a dog or a cat. Super simple. We'll be working on a small data set, and you'll see how it works. But this is what we'll be building at the end, and you'll be able to build at the end too. So stay tuned till the very end, and yeah, we'll make it easy and decouple it. But before moving on to anything and actually to the implementation part, I want to go ahead and discuss a couple of things about machine learning and the idea behind machine learning. Okay. So, I just forgot to mention, you'll now see captions under the slides right over here. So it might become a lot more easier for folks to follow along. So let's continue with what we were talking about, the idea behind machine learning, and how is machine learning any different from the traditional technologies, what we'll be discussing in this short little segment. So I'm sure all of you might have worked with traditional programming, traditional languages. So let us say we want to make an algorithm to differentiate between cats and dogs, which is what we'll also be building at the end. But as of now, I want you to think of making an algorithm to differentiate between cats and dogs with the programming you already know, the traditional programming you already know. Maybe you know Java, C, C++, or anything else. I want you to think of how you would be making an algorithm in it to differentiate between cats and dogs given the images. So traditional programming has been the bread and butter for developers for lots of years. And what you do in this is essentially you express rules. These rules would work on the data. So, uh, so I would give, if I wanted to build this kind of program for with a traditional programming, what I'd do is I'd give it a lot of rules. These rules would work on the data and get me the answers. So these rules could be ifs analysis, a lot of if analysis, and data would be the images of cats and dogs. So as an example, I'll be saying something like if in an image you see something like let's take a simpler example to better understand the idea of traditional programming and how it is different. So let's take another program which we want to make. For example, we want to make a program which, given an image, can classify if it is an orange or a banana. So how would you do that with traditional programming? You would give it a lot of rules. So what rules can you think of? Quick. So what I can think of is things like if the image has orange color in it, maybe it's an orange. If the image has yellow color in it, it's a banana. And that's the basic rule I can give it to know if an image is orange or banana. And then I have a lot of shapes and all of that. So you get the idea, a lot of if analysis, give it a lot of rules. All of these would be hand coded, a lot of work. ML then turns this around. It flips the axes. So like instead of we writing a lot of rules in the codes, like I just mentioned, why don't we give it a lot of answers? We give a lot of answers to the machine. So for our example, for the program we want to build today, I give it a lot of data. So recall what I said. The data is a lot of images of cats and dogs, a ton of images of cats and dogs. What ML does is it also asks me for the answers to this. So I need to have labeled images. So for each image, I should also pass into the machine the answers. So which image is a cat, which image is a dog, I also need to pass that in. And after I pass in a lot of data and answers, with machine learning, the machine would rather infer the rules that map one to another. So maybe now you can understand how machine learning is different from traditional programming. So I'm essentially giving it a lot of data, a lot of the answers for that data, and machine learning will try to figure out some pattern between the data and the answers and figure out the rules for us. So earlier we had hand coded the rules, but now the machine learning algorithm would figure out the rules for us. And what we can do is when we actually want to deploy this or want to use this machine learning algorithm, we'll use these rules to get inferences or new answers on data which the machine learning algorithm hasn't seen earlier. So I hope you are now understanding the paradigm with machine learning. So let's take another example to see why this is something you would want to care about. So let's talk about activity detection, which is a pretty fancy problem to talk about and pretty cool too. So how would you write code to say that this is what someone walking looks like? Any guesses? Maybe you have access to the speed. So you say, with a traditional algorithm, so you say, if they are moving below a certain speed, they are probably walking. So something like a simple if else. If speed is less than 4, the person is walking. Simple till here, no problem. Okay, then I have another person who's running and I want to do activity detection. So you could say simple again. if they are above a threshold value, let's say if a person is less than his person speed is less than 4, he is walking. If a person's speed is more than 4, they are probably running. But what about biking? They are probably faster at biking, right? So again, uh, if then code could be written and now you have activity detection, great. But now your friend comes to you and he loves golf, and you want to write activity detection code for golf, but you have never written rules for it. So your algorithm cannot do anything when it sees image of a person playing golf. It cannot figure out that this person is playing golf because you have written the rules for it. So I want you to remember this image which I talked about earlier, how machine learning takes in the data and the answers to give us out the rules. I want you to remember this again. So with machine learning, what we would do in our activity detection concept is all you need is sensor data from people who are walking, running, biking, and even golfing, which in my case is only sort of golfing. You would then train a neural network with this data. So what you're doing is telling a computer, this is what walking looks like, this is what biking looks like, this is what golfing looks like, and so on. After which, the computer would try and figure out the rules which make this binary data which you see, which is sensor data for all of these 4 activities, just some example data, and convert it into the label. So the machine learning algorithm would try to figure out the rules to go from the data to the answers. So I hope this makes sense and lets you now know that why why writing machine learning algorithms is any different from traditional programming and when can it be effective. So with that, let's start building something. And as I said, this is not going to be just something where you sit and listen to me, listen to a boring kind of lecture, but it would rather be something where we'll also build something together, and you will be able to try it out after the talk too. So with that, you know the difference between machine learning and traditional programming, how it is better and all of that. So what are we up to now? So first off we'll try to make a machine learning algorithm under which we'll try to input the data. So I'll show you how you can input the data to a machine learning algorithm, because remember, you need to input the data and the answers to a machine learning algorithm, which would then give you the rules, right? After which we'll take a look at how you can build and test a model or a neural network, and you will do that in this talk too. After which we'll take a look at overfitting and data augmentation. And do not worry at all if you don't understand these words at this stage. We'll take a look at them in later part of this talk, and you'll definitely understand it over there. So don't worry about the last 2 words over here. So let's go on to the first part, which is understanding the data. So as I say this very often, and you can even quote me on this. To make a successful machine learning application, what you need is not the machine learning algorithm itself, but data. So it matters more if you have good data, if you have a lot of data, than the machine learning algorithm in some cases. So everything in machine learning is pretty much running on data. So first off, I want you to understand the data. That was pretty obvious. So, so if you remember what we'll be building today, we'll be building a simple algorithm which can, given an image, say if it's a cat or a dog. So what would our data be? Any guesses? Well, I've already said this. You just have to type it. Any guesses? Come on, folks. Yep, that's correct. It would essentially be images, a lot of images of cats and dogs. That is essentially what my data would be. So this is what it would look like. I have two directories in my uh, I have two directories. One is called the training directory. So what I'll do is I'll take all of these images in the training directory, which are further classified into cats and dogs because I have two classes. So I'll take all of these images in the training directory and use my model to figure out rules using the images in the training directory. I'll also have a couple of images in the validation directory. So I'll try to validate my model on these images, or rather test my model on these images. So I can know how well my model is performing in a kind of real life scenario, images which it has not seen earlier. So I also want to test that, and that is the reason we are using a validation directory. You'll understand this in greater detail in some time, but yeah, you can as of now just understand that we are using this validation directory so I can know how my model is performing on images which it has not seen earlier. So with that, let's move on and see some real code and how you can do it. So the data set which I'm using as of now, it has 3,000 images, 2,000 training images, 1,000 validation images. So you can see, so I've just shown the kind of images which will be the number of images which we'll be working with today. So since a lot of you might be trying machine learning for the first time, we'll be working on a super small data set with just 3,000 images of cats and dogs. So moving on to some code, let's see some code on the go. So as you might have guessed by now, we'll be using TensorFlow today, which is a pretty popular deep learning framework and allows you to build neural networks very easily. So if you know a bit of Python, I've just imported a couple of libraries over here, nothing great over here. What I do want to tell you right now is, so I have all of these images in my computer, but I need to send it to my machine learning model, right? I need to send all of these images and if each of these images is a cat or if each of these images is a dog to the machine learning algorithm, right? So so I'll first have to do a couple of transformations to the image so I can send it over to the machine learning algorithm. So in this case, I've just mentioned a couple of parameters for that. As of now, I don't want you to worry about the batch size and epochs, which you can see over here, but I would want you to understand image height and image width. So I'm just telling you, I'm here just telling my model that it should be expecting images which are 150 pixels by 150 pixels. So all of the images which we'll be working with today are 150 pixels by 150 pixels, and that is what I'm telling my model over here by specifying the image height and image width. So now so as I said, we now need to send all of this data, send all of these images to the model, so or the machine learning algorithm. So we need to do some data preparation or prepare the data to feed it into a neural network. For this, we need to format our images into accurately pre-processed floating point tensors. So it's essentially saying that each of the pixel values, since a computer would not understand a PNG, but rather pixel values. So I'll need to first read images from the disk. After which I would decode the contents of these images and convert it into a proper RGB content, have a proper RGB content with it. Then I also need to convert all of these images into floating point matrices or tensors. A tensor is essentially a sparse matrix, but if you know what a matrix is, uh, yeah. So I'll also need to convert this image into a matrix which has all the pixel values, which is essentially how an image is represented, right? By the pixel values. After which, I also need to rescale the tensors. So for most machine learning algorithms, as of now, I would like to give this as a tip to y'all. So if you work with an image essentially has pixel values between 0 and 255, right? Image has pixel values between 0 to 255. I'm sure all of you might know this, but with machine learning, our neural networks prefer to deal with smaller values. And they usually perform well on smaller values. So for this, I'll convert values from 0 to 255, the image values, the image pixel values from 0 to 255 to 0 to 1. So I need to perform all of these 4 steps, after which I can feed my data to my neural network. Seems like a lot of work, but fortunately these tasks can be done with the image data generator class provided by TensorFlow. So we'll take a look at this. So what it essentially allows you to do is read the data very easily, read image data very easily, and process them into appropriate matrices. So let's see how this works in code. So first off, nothing new over here. I'll be using, I'm simply importing the image data generator class from TensorFlow. So I'm simply importing it right over here, after which I can start using the image data generator. So you might remember I said that neural networks like to work on smaller values, and I want to convert my pixel values from 0 to 255 to 0 to 1. So how do I do that? Image data generator handles it all for me with just a simple line of code right over here, where I'm saying it rescale equal to 1 dot slash 255, because I want to divide everything by 255, convert 0 to 255 to the range of 0 to 1. Simple. And image data generator makes it a lot simpler for you, in as you can see over here. After which, I have the train image generator, which is what I just defined, the image data generator object which I just defined above this line, and I'm asking it to flow from directory. So remember the kind of data directory structure we had earlier. We had a training folder which had 2 other folders, cat folder and a dog folder with their respective images. So using the dot flow from directory, which you can see, what image data generator with TensorFlow would do is it would load in all of these images and accurately label them for you, all with just one line of code. After which, okay, so I told it that you need to get images from the directory, but I need to tell it which directory I want the images from. So I'm simply telling it that all of my training images are present in this training directory, which you can specify. Finally, remember earlier I was telling you that I have images which are 150 pixels by 150 pixels. So I can simply specify the target size right over here, give it the image height and width, so it knows it should be expecting images with size 150 pixels by 150 pixels. And then you might have also seen the batch size. which I earlier told you not to worry about. So image data generator, if you see right over here, is essentially taking images, and these are a lot of images. If I go by the numbers, I am getting 2000 training images. So I want my algorithm uh, to take these images in batches. So what does batches essentially mean is I'm taking first 32 images. I'm then taking another 32 images and so on. So I can simply specify that by the batch size. It could well be 64 images, 128 images, or whatever you feel like. Uh, there are a couple of rules for selecting a good batch size, but I'll not go into them in this introductory talk. So that is what the batch size parameter does for you. And we had already specified this earlier. After which you can also see the class mode equal to binary. Now this is super simple, and I think a lot of you might have guessed this because of the name binary. So what does binary mean? Any guesses? Well, you know it. It means two, right? 0 and 1. There are two numbers and so on. So if you see why are we writing binary over here? We essentially want to classify the image in two classes, cat or a dog. Those are two classes. So I'm essentially telling it that you should be expect that I want to take images in two classes, cats, dogs. Those are the two classes which we are working on right now. So I'll simply specify it class mode equal to binary, which will do the which will help me specify that. And similarly, I had two folders, right? A training folder and a validation folder. So if I go to the previous slide, bear with me. If I go to the previous slide, I can see that I have taken in all of the training data, all of the training images. Well, I also need to take in all of the images in the validation directory, or the images which my model will not be trained on. So I'll also do the same process for all the validation images. So you can see same piece of code, but I've just changed the name from training data to validation data. So with that, you have built input pipeline, and we'll also see this in action. I'll run all of this in front of you and we'll try it out. So yeah, we'll also be doing that. But this is how you essentially build a data ingestion pipeline with TensorFlow. So with that, I've taken in my data, but now I want to build a neural network. So let's go on to building a machine learning algorithm, a proper neural network, which can work on the data. So this is the most interesting part because this is where we'll actually be building a neural network. So I wanted to take a look at this piece of code. If it looks a bit intimidating to you, do not worry about this. We'll break it down line by line and you'll understand everything from this. So first off, I want to make a model, and I'm specifying it the input shape. So first I have the flatten layer. So there are three layers in this model. The first layer is a flattened layer, the second layer is a dense layer, and the third layer is also a dense layer. We'll come to what these all mean, but what I do want you to take a look at is the numbers highlighted over here. So first off, you can see input shape equal to 150, 150, 3, which is highlighted. So I'm sure you have already guessed what this means because, well, input shape is written, but this is essentially you telling the neural network that you will be getting data which is 150 by 150 pixels, which is our image size, 150 pixels by 150 pixels, and it will have the 3, and I also see a 3 in front of it. So Can you, so do you know why the 3 is over there? Anyone? It's super simple, but can you make any guesses? Why do I have a 3 over there? My images are 150 pixels by 150 pixels. So why do I have a 3 over here? I'm seeing your comments. And we have got correct answers right away. Yep, that's right. You got it right. 3 axes, 3 dimensions, RGB. That's correct. So you can also call these color channels. So you can call these color channels too. So we essentially have 3 color channels over here, which is RGB, or 3 axes for the color. Uh, yeah. So I'm essentially specifying that to the model right away. Oh, I just skipped a slide. Okay. And in the end, I again have 2. Now, what is this 2 for? It's essentially telling my model that it should return out 2 outputs. It should, we'll see what this means and how you can infer from it. But because we have 2 classes, we want an image to be classified as a dog or a cat, which is, there are 2 classes which we want the image to be in. That is why the 2 is there at the end. After which we have 5 and 2 dense neurons. So at the start, I told you that we have 3 layers in this neural network, and you can have multiple layers in this neural network. You can extend this, but as of now, for the super simple neural network, we have 3 layers. First is the flattened layer, which we'll see in greater detail in some time. Then we have 2 dense layers. So dense layers are essentially fully connected neurons in a neural network. So the first dense layer has 512 neurons in it. So you'll see how all of this looks, but you can, as of now, understand it as 512 units in the second layer. In the third layer, we have just 2 units because third is our last layer, and we have 2 classes to classify into. So how this looks like is, I essentially have my image. So what flatten does is, my image was 2-dimensional, right? 150 pixels by 150 pixels. Flatten converts all of this into a single dimension. So you can essentially understand it as making a 2D image 1D. And how do you do that? Simply take all of those pixels and stack them side by side, which is essentially what flatten is doing. It is converting a 2D image into 1 dimension. So you can see that the first layer right over here, it is 1-dimensional layer with all of these alternating black and white values, which are essentially my pixel values. In the next layer, which you can see in this image, I have 512 neurons. And each of these neurons is essentially a function. If you remember some mathematics, you'll tell me that a function is simply something which converts input to output. So simply putting a mathematical operation on this. And then we have the last 2 neurons. So essentially how this works is, since it's a fully connected layer, as the name suggests, my second and third layer were fully connected layers. So as the name suggests, all of these inputs will pass into each of these layers. So all of these 5 and 2 neurons which you see over here have some internal variables which are initialized to random states. And when we start passing pixel values to all of these functions, their job is to understand and guess what the output is. So for example, F0 grabs all the pixels, F1 grabs all the pixels, and so on. And if those functions think like, okay, these look like dog, then the function would maybe pass a greater value to 1, which in this case represents a dog. It could also be the alternate thing, 0 could represent a dog. But just for simplicity and giving you an example, if these neurons learn from the data, and then if they think it's a dog, which here is represented by 1, these functions would pass it into 1. And if it's a cat, the other way around, as you can see in this image. So now I understand. So now I hope you have some idea about how a neural network works. And this is showing you how a single layer in a neural network works. So a neural net, and then you can just do this multiple times and build a neural network with a lot of layers, also increasing the complexity. So all of these functions would essentially make out the rules for the machine learning algorithm. So there you have it. You made a very simple model. But if you see, I just made a model, right? I still need to train it on the data, which is I need to pass in the model all the images. I need to pass in the model all the labels and allow the model to do all the computation and figure out the rules for me. So let's go on to that part. So next up, we have something called model that compile with TensorFlow, and this is pretty important. I want you to take a bit closer look at this. The optimize and loss functions we'll be talking about. So, but before that, what do you think this piece of code does? Dot compile. Well, it doesn't convert code into bytecode, but think about these two parameters, optimizer and the loss. These are the most important part of doing a machine learning problem. And most of the academic research is also based on this topic, uh, optimizer functions and loss functions. So remember those 5 and 2 neurons. So all of these 5 and 2 neurons are first initialized with random states. So if they are randomly initialized, there is 1 in 2 chance it would guess an image correct, right? Because an image could be either dog or a cat, and I have initialized it at random. So there is 1 in 2 chance that my model could get it correct. So what the loss function does it, since I have initialized all of these 5 and 2 neurons at random, what a loss function does is it calculates thousands of times how good or bad a model is. So remember the training part, which is where first the loss function will tell the model how good or bad it is. So for the very first time, the loss function will tell the model that it is performing really badly, because well, I'll give an image of cat to the model, and the model will give me some predictions, tell me if it is a cat or dog, but model is not yet trained, so it is bound to perform very badly, and the loss function will tell it how bad the model has performed. All of the loss function data or all of the loss function computation goes to the optimizer. So, well, loss function told me how bad I performed, but I also need to improve, right? My model needs to improve. So optimizer does exactly that. Optimizer takes the loss function data, which is how bad my model has performed, and tries to make the model better, or tries to improve those random states in our 5 and 2 neurons. So that is pretty much how the optimizer and loss function work, and that is pretty much how training takes place. So you can also see epochs written over here. So epochs are essentially how many times should I do this. So one epoch is uh, so if you take a very simple case like we took over here, one epoch is usually model model does a prediction on which the loss function tells it how good or bad it has performed, passes the data to the optimizer, which which tries to improve the random states within the neurons, and this continues on and on for multiple times. So since I have here specified 100 epochs, this process will continue for 100 times. And that is what essentially epochs means. Okay, so now you also understand what epochs means. I earlier told you do not worry about epochs part. So now you probably understand what epochs means too. So let's go ahead and first talk about that was essentially how a neural network works, how loss functions work, how optimizers work, how to define a super simple neural network. But we want to we want to make classifications on images, right? And making classifications on images is a pretty hard task, since it is us humans who find it easy to make classifications from images, but you essentially need to tell computer rules, strict rules, that what should be there in an image to classify it as a cat or a dog. So let's take a look at how that works. So the major part about how image classification works is using a filter. So I want you to move on with me, and let's take an example in this image. In this image, I take I take 3 pixels by 3 pixels from this part in the image, which I've highlighted right over here. And let's say, for example, the values of these 3 pixels are uh, are the ones which are written on your screen. So I'll pick the pixel which is in between all of these. So let's say I'm talking about the pixel 192. I'll pick out the 3 by 3 pixel values around it. Then I have a filter, and what I'll do is I'll essentially multiply the first row, first element of the filter. So essentially, this is what I'll be doing. I'll multiply the first row, first element of the filter to the first row, first element of the pixel grid I had chosen. The second row, this element of the filter. So filter is also, as you might have understood, filter is also a couple of values. So I'll take this value from the filter, multiply it with this one, and so on. I'll do for the complete filter values and add all of them up. So I'll not talk about the proof of why this works, but I do want you to see an example to tell you how efficient this is and how well this works. So some of you might be wondering what would happen if I just multiplied a couple of numbers and just added them up. So after multiplying the filter, I'll come to that. So after multiplying the filters with the pixel values, I'll replace my original pixel, which was 192, the pixel value, with the one I just calculated. So let me rather show you an example of this, and you can decide how well it works. So on the left, I have an image. I take each pixel from this image and use this filter definition on top of it. So you can see this filter which I have. I use this filter on this image on the left. And if you see the output which this gives me, which is the image on the right, I hope you can make some pattern out of them. You can see that all the vertical lines in the image are actually highlighted for me. And this is an example of the power of filters. So I just did all the computation which we discussed about in the previous slide, applied it on the image on the left, and this is what we ended up with, all vertical lines highlighted. And I can do similarly with a slightly different filter, and all the horizontal lines in the image are highlighted. So I can essentially get features from the image or distinctive factors from the image. So you might have now understood the power of filters which form the basis of a convolutional neural network, which you uh, mostly use for image classification. Now, a question which I often get is how difficult it is to implement all of this. We talked about a lot of stuff. We talked about a lot of calculations, about how filters work. So do I need to write long code to implement all of this? Well, the answer is no. You saw how easy it was to make a neural network, train it on some data. That is what we'll also be doing that with TensorFlow, seeing how you can implement filters in TensorFlow, see how you can implement convolutional neural networks in TensorFlow. So also it makes it super easy for you. So let's see how I can actually implement all what we talked about. So here you can see I have a con2D or a convolutional layer. So remember earlier I had just 3 layers, which is the flatten, dense, and dense. Just 3 layers. Those 3 layers are at the very bottom now. Now I have added a couple of layers to the code which I had written earlier. So if you can see, the con2D and the max pooling 2D are essentially pasted 3 times. And we'll break this line by line. You'll understand each bit of it. So first off, I have a convolutional layer. What do I first need to tell it is the number of units. So I simply tell it to use 16 units. So earlier, remember I had 512 units. For a convolutional layer, I'm using 16 units. Then I need to specify the filter I want to use. So I want to use a 3x3 filter, and that is what I am specifying in the next value, which is 3,3. Next up, I'm also telling it about padding and activation. We'll soon come to that. But you can also see the input shape right over here. And the input shape is 150 by 150 by 3. By now, you already know why it is 150 by 150 by 3. So I'll not go over it again. But I also specify the input shape simply right over here. So you might also see we have a new kind of layer over here. We have 2 new layers over here. One is the con2D layer, which was new, and we talked about it. And next up, we also have a max pooling 2D layer, which is new. You might not have heard about it. So I want you to tell you what the max pooling 2D layer does. So with the con2D and applying the filter, which is essentially what a convolution layer is doing, I have a lot of data. I need to find some way to compress the data, which is compress the image which I get from it without losing, and I also don't want to lose important things, right? So let's say my filter has highlighted all the horizontal lines for me. I want to do something to reduce the size because it gives me a lot of data. I want to do something to reduce the size of it so I can work with it. But at the same time, I don't want to lose all the highlighted horizontal lines, right? So this is how we do it. So what max pooling 2D does is, this is, let's say, an image with all of these pixel values. I have a max pooling 2D layer of 2,2, as you saw in the previous slide. So I'll take a 2x2 grid from this image. I have a 2x2 grid, as you can see. What I'll do is I'll take the maximum pixel value from this 2x2 grid. So in the first example, you can see 0, 64, 48, 192. The maximum pixel value is 192. So I'll take 192, keep that pixel with me, and discard all the other pixel values. And I'll repeat this for each and every 2x2 grid which I have. So here I can form 4 2x2 grids, and I've shown the example. And then you can see that I converted a 4x4 image which had 16 pixel values to a 2x2 image which has 4 pixel values. I essentially reduce my data by a size of 4 by a size of 4. But I also did not lose all the important stuff in this, because all the pixels that were highlighted, all the pixels which are pretty much highlighted or are the important features, I have kept them. So that is the idea behind max pooling 2D. And let's take a look at uh, max pooling in action. And this is the same old example which we looked at for filters and how filters work. And this time I've not just applied a filter, but I've also applied a 2x2 max pooling. And this is what I get with it. Pretty impressive, but it has reduced my size by a factor of 4. So that is pretty much the idea behind max pooling. After which I do the flatten. After which I want to talk a bit about the flatten layer. So now I think you already know what flatten means. I already told you converts 2D images to one dimension. Let's actually see how this works, and let's take a look at, let's say this is my pooled feature map, which is essentially my images after the max pooling. Once I flatten them, it's simply converting a 3 by 3 array to a 9 by 1 array. So I simply now have one dimension instead of two dimensions. And that is what the flatten does for me. Having told about that, we'll come back to our convolution layer. So there's a reason I actually talked about max pooling 2D first, so you can better understand how all of this works. And now remember, I had told you that do not worry about the padding and activation in the convolution layer, which you see right over here. Yeah. So let's talk about the padding and activation, which I see right over here. So what the convolution layer is doing is it's essentially applying a 3 by 3 filter. Let's say this is my input image. So I have a simple question. Can I apply the filter on the bottom right pixel, which is highlighted for you? Can I apply this 3 by 3 filter on the bottom right pixel? So remember, a filter needs 3 by 3 pixels. Since it's a 3 by 3 filter, it needs 3 by 3 pixels around the pixel you're working on. So can I apply this on the bottom right pixel?
There's a 10 second lag, so to
Okay. So I'll talk a bit about so if you see how these filters work is, I essentially would need to apply the filter on the bottom right pixel, which you see right over here. I would essentially need I would essentially need some more pixels, right? I would need a pixel right over here, right over here, right over here, right over here, because it needs the pixels around the pixel you're working on. And I don't have them because that's the end of my image. So I can't actually apply the filter on the bottom right pixel. So the padding equal to same, that is what it does for me. Uh, so the output which I would have after applying a filter would not be a 4 by 4 image, but would be a 2 by 2 image. I'm essentially losing all of the uh, I'm essentially losing all of the border pixels right over here. So that is what padding allows me to do, is lose all of these border pixels, so the filter can work. Next, I have the activation function, which are specified to ReLU. And this is again really important R2. So what activation functions are used is if you stack a lot of these layers, but you only then you would end up with a linear relation, right? I'm stacking multiple linear relations, I'll end up with a linear relation. Instead of that, I can use filters to introduce some complexity in it. So I want my neural network to be able to handle complex data, to be able to come up with complex relationships, and that's where the activation function does the work. So we have a lot of activation functions. These are the 6 of them. We have sigmoid, tan hyperbolic, ReLU, which we are using right over here. Since we are using ReLU, and it's super simple to explain, what ReLU does is if you have a positive input, it takes the input. If you have a negative input passed to it, it will simply discard the input and uh, and default to the 0 value, which is the activation which we are using right over here. So you can also try out with all of these different activations, and they are super simple to implement. Having talked about that, I made a new model right in front of you, which works well on images, but and now I also need to now I also need to pass it in the data and actually allow the model to train. So that is what I'm doing. You now already know what an optimizer and loss function works. So I'll specify the optimizer and the loss function, and then I have metrics right over here. So I'm telling it that whenever you are doing the training process, you can tell me you should be telling me what my accuracy is. So I'm interested in how accurate my model is. So that is what I'm asking it to tell me while the training is on. So this is the model you have built: convolution layers, max pooling layers. It has 3 convolution layers and then 2 fully connected layers. This is a neural network we just built to perform image classification on dogs and cats. So I can simply use the model.fit, which actually performs the training process. And now you already know this. First off, I'll pass it in the training data. I'll pass it in the number of epochs. I'll pass it in the validation data, or the data we had in the validation directory. And that's it. That's pretty much what I need to do to actually train my model. So seeing the outputs of this, I get a graph looking like this. So let's see the accuracy. So my accuracy is well over 95%, which is pretty good. But if I see my validation accuracy plotted with the orange, you can see that my validation accuracy is just around 75%, which is a bit bad because my model is not able to perform well on data it has not seen before. So if you give it a new image of a dog or a cat, the model won't be able to perform as well. And we don't want to do this, right? We want the model to be able to perform well on new images. So I need to fix this. And I can see a similar pattern with the loss function too. My validation loss is very high and my training loss is pretty low. So I want to fix this. This is really bad for my model. So I want to try and find a way to fix this. And this scenario is actually called overfitting. Now we'll understand what this means, why it is bad, how you can fix it, and we'll make it super simple so you can very easily understand and implement it. So what this essentially means, you now already know what overfitting means. The model is not able to perform well on new data. So how can we fix this? So the first thing, of course, is I give it more data or more kinds of data. But this can often be costly. So I might have to spend a lot to get more data. So uh, today we'll take a look at the other 2 methods to solve this. So the first is using data augmentation. We'll go through it in detail, and using architectures that generalize well. We'll also take a look at it. So first off, I want to talk a bit about data augmentation. So with data augmentation, the idea is super simple. I take an image and I perform some transformation on the image. After which I have the transformed image pass into the model 2. So let's see an example of this. I think it would be better to show an example of this. So this is an example of a transformation. I took an image of a cat, I horizontally flipped it and passed both of these images to the model. So the model has more data, which is essentially the same image, but with transformations applied on it. I can also rotate the image by some extent. I can zoom into the image and so on. I can do all of this very easily with the image data generator, which we worked with earlier. So now you know most of this code. We talked about most of this code in the previous slides. But what I do want you, oh, sorry. But what I do want you to know is, I just skipped a slide, sorry. But so earlier we had the rescale, which is nothing great. It just allows me to convert 0 to 255 to 0 to 1. And then I have a couple of other parameters. So the first is the rotation range, which is telling it to rotate it to 45 degrees, rotate each image up to 45 degrees. Then I have the horizontal flip. So I want to horizontally flip images in my training data and pass them again to the model. So again, image data generator makes it super easy for you. And after this, I can simply take in all of my images through the same code. This is the exact same code. I do not need to make any changes to allow it to flow from the directories or take the images from the directories. So that was about data augmentation, and it was pretty simple to understand. You essentially make transformations. And next we also have dropouts, which I'd like to discuss in this talk. So this is also another technique to overcome overfitting. So what this does is it essentially, so you remember those neurons which we had in our neural network. So what does it do? What it does is it essentially drops some of the output units from the applied layer. So while the training is going on, I'll just switch off some of these layers, some of these neurons. And what this will allow me to do is it will allow other neurons to better learn or better generalize for that particular training step. So it's pretty simple again. I'm just switching off a couple of neurons. And again, TensorFlow makes it super simple for you to implement this. You just add dropout followed by a number. So this number is essentially how many neurons you want to switch off. So I'm saying 0.2, which is essentially I want to switch off 20% of the neurons. And that's how simple dropout is. So with that, we have also overcome the overfitting, and the model is ready to go. I can also simply test my model. So you see a lot of code over here. Do not be intimidated. This is just some simple code to take in images and all of that. But what I do want you to see is the last if and else over here, which is essentially telling that if my model gives me an output of more than 0.5, so my model will output a number between 0 and 1. So if it's more than 0.5, the image is of a dog. And if it's less than 0.5, the image is of a cat, and so on. So that's just some super simple code you can use for testing the model. So with that, let's actually try this out in practice. Let's see some code. Let's try it out right now. So this is the link you would want to go to for the demos. So also note that you don't need to install anything in your system or don't need to make any setup. You can directly run this online in your own browser without any setup. So and it would work similarly. So I'll do the browser approach itself. So it would be a lot more easier for you. But this is essentially where all the code accompanying this talk, where you can find all the code accompanying this talk. So we definitely want to make a note of this URL on the screen right now. Okay, let's go on to demos. So hang on with me. I'll quickly switch my screen, go on to my demo screen. Oh yeah, it's a GitHub repository. Someone in the chat mentioned, thank you. It's a GitHub repository where you can find all the code, and you can also find one more example. So it can possibly become better if you want to try out a couple of more things. Let me, yeah, here it is. Okay, let's go from the beginning. So I'm running this in Google Colab, which allows you to do everything which I'm doing right over here in the exact same way in your browser without having to install anything. So here is the training process actually takes some time. It takes around it takes quite some time. So I just ran it just before this talk, but we'll see the live results. So I can see my image height and image width being specified to 150 by 150, 150 pixels by 150 pixels. Then I've just made some variables to make it easier for me. Just some variables, nothing great over here. But what I do want you all to see is, oh, yeah, I just forgot to do this. I just forgot to zoom in. Yeah. So now you might be able to see it a lot better. Sorry for not zooming in. So you might remember how we perform data augmentation with the image data generator. So this is where I'm doing it. First, I want to rescale my image from 0 to 255 to 0 to 1. That is what I'm doing right over here. And then I'm specifying all the data augmentation properties. So I wanted to perform horizontal flips. I wanted to perform a rotation and so on. So this is for the training. I'll do the similar thing for the testing directory which I have. So I'll also do the similar thing for the testing directory which I have. After which I can start loading my image. So for loading the image in the training directory, I first pass in the training directory itself. Pass in the path of the training directory. Tell it that the images are of the size 150 pixels by 150 pixels. Tell it to take in 20 images, which is my batch size. And you also know what the class mode binary means. I perform the same for the validation directory too. So I can see that I have 2000 images belonging to two classes in the training directory, 1000 images belonging to two classes in the validation directory. Finally, let's build the model, which is, I think, the most exciting part since we are actually building the model. So first up, I have a convolution. Oh, sorry. First up, I have a convolution layer, which has 32 units, 3 by 3 filters. It has padding, and I have the ReLU activation function, followed by a max pooling layer of 2 by 2, which is then followed by a dropout, so I can reduce the overfitting, which we talked about. And then this continues. I have I have 4 convolution layers right over here and 4 max pooling layers right over here. After which I have these 2 dense layers. So the first dense layer has 5 and 2 neurons, and the last dense layer, since it's the output one, this layer will be giving us the output. It has just 1 neuron, which will give us a value between 0 and 1. So if the value is more than 0.5, it's a dog. If it's less than 0.5, it's a cat, and so on. After which, I'll give it the loss function and the optimizer. I'll give it the loss function and the optimizer function. After doing that, I can start to actually train my model. To train my model, I can simply use .fit, pass it in my training data, pass it in the number of epochs, pass it in my validation data. And that's how simple it is. And as you can see, it takes a lot of time to do the training part. It would also take a lot of time to do the training in your browser. But if you're using Collab for the first time, you might want to use a GPU. So I can just go to change runtime type and I can use a GPU over here. So GPU is essentially a hardware accelerator which allows me to do this faster, but still it takes considerable amount of time. So after 100 epochs, I get a good enough accuracy of a good enough validation accuracy that's on images the model has never seen before of around 80%, which is pretty good for considering we just trained it for 100 epochs. After which I can also I can also see if I'm not performing overfitting. So I can see my accuracy on the data which my model has already seen also increases as the number of epochs increases, and my model also performs very well on data it has not seen before. So I can say this model is doing a good job as of now. Okay, so I have a, I have an example to test this model out live, and let's try to do that. I simply have an if statement right over here, which says if I get an output of more than 0.5, it's a cat. If I get an output of less than 0.5, it's a dog. Super simple. I'll pass it in an image to see how well this works. And let's pass it in an image. Let's see what it can tell me. And it tells me that this was and I passed it this image called cat2.jpg. So let's see which image this is. Give me a moment. I'll quickly switch my screen so you can better see it. Okay, here it is. So could you bring up my screen? Thank you. So here you can see I have a couple of testing images for you to play around. And I can go to cat. I had this image which I uploaded earlier. It is called cat2.jpg. This is what I uploaded, cat2.jpg. Let's see what this image is. It's a cat image, you know from the name, but this is the image I passed into my model. And see, this is the output it gave me. It was almost 100% sure that this is a cat image. So I can say my model performed really well. And that's about it for the demo. We also tried running the model live. You can go ahead to the GitHub repository. Simply click on the Collab button to open this in Collab, run the demo live, try it out on your own images, and let me know how it works out. So that's pretty much it for the demo, for the talk. I hope you enjoyed it. I hope you learned from it. And with that, if we have time, I leave the time part to the organizers. If we have time, I'd love to take any questions which come up.
Hey, yeah,
Thank
that
you
was a
very
nice
much.
talk. Okay. Yeah, you can continue, Sukrit.
Yeah. It was very interesting, and now we have fireside chat with Mr. Rishit Dagli. I call upon Pulkit and Shreya for the fireside chat.
Hello, am I audible?
Yeah, you are audible.
Yeah. Hello, Rishit.
Hi, Pulkit.
Hi. Okay. Basically, we'll start. Okay. How did you come across AI and ML, and who was the inspiration behind this field?
Oh, that's actually a pretty good question. For me, it's been pretty interesting as a journey too. So I'd love to talk a bit about it. So I earlier used to work with robotics and with Arduino's, Raspberry Pis. If you know what I'm talking about, if someone has done kind of robotics stuff earlier, you know what I'm talking about. So I earlier used to love robotics and and then I got an interest into programming for embedded systems, working with C, C++, and all of that stuff. And it was just a course which I took, I believe, which showed me that okay, it's not just how machine learning is different from all the traditional programming we have been doing and all of that. So that's when I kind of uh, started to love machine learning, and after that, I there has been no looking back. I've just loved machine learning and tried to explore more.
Okay. Nice. Cool. Okay. Over to you, Shreya.
Hello, I'm Shreya, and I wanted to ask, like, what is your biggest challenge as a teenage mentor?
Uh, a biggest challenge as a teenage mentor, that's a good one too. Uh, so as of now, I would say it becomes a bit difficult for me to manage my time because so I'll be pretty frank over here. I had my 10th board exams last year, so it was just 2 months, or I think a month, I'm not sure, 1 or 2 months before the board exam, and I had a talk which I had to prepare for. So it becomes a bit difficult to manage times with school exams and all of that. So I think that's the biggest challenge, which I'm also struggling with as of now.
Okay. Actually, we have a question from the comment
Sure.
section. Sir, any tips? I mean, Rishit, any tips regarding this topic for students from bio background? Do you have
Okay.
any suggestions for them?
So there are actually a lot of cool stuff which you can do with things like X-ray recognition or finding out diseases from X-rays, which is just a simple example to give you some idea about. But there's a lot of cool stuff you can do with uh, or do in the field of biology with AI. You also have things where you can use a pattern on genes, perform AI on them. So I so as so to start with this, I recommend you to uh, take a look at mathematics, since that's what forms the base of machine learning. And I tell this a bit too often, but yeah, I believe that machine learning is essentially founded on mathematics. It's essentially some fancy mathematics. So if you really want to understand machine learning and try to apply it for things which you are interested in, biological problems, at first to get started, I would recommend you to get a good grip on mathematics.
Earlier, you had mentioned that you struggle with your 10th board. So, how do you advise us to manage both creating projects and managing studies?
So uh, one thing I would say is I was in my free time. I always used to build projects and not do some other stuff like not do some other stuff. So because well, I like to build projects and build systems or so on. So I so if you really like doing something, maybe could be AIML too. Um, for me, it was just something that I did in my pastime. So that's how I pretty much manage my 10th boards plus creating projects, doing talks, learning more on the way too.
Okay. So basically, how do you prioritize topics? Like, how do you what do you think?
Prioritize topics for learning machine learning, or do you mean that?
Yeah, AI and ML. Yeah.
Okay. So, uh, since you asked about learning machine learning, um, I already mentioned this in our question earlier, which is you need to get a good grip uh, of mathematics for sure. I had always been interested in mathematics from past four grades, and that's how I kind of covered all the engineering syllabus mathematics in 8th standard, 9th standard too. I was always interested about mathematics, and that's how I actually came into machine learning too. So you will find a lot of people saying this, and it's 100% true. You need to start with mathematics for sure, and I would give it the top priority. So maybe you can take a look at some topics like linear algebra, calculus, pre-calculus stuff. So I kind of give more importance to all of these topics, and you going over all of these topics. And when it comes to actually programming MLAI systems, there are a lot of
Okay.
choices. Today we took a look at TensorFlow, which is the one which I've been working most on and my personal favorite. But there are a lot of choices which you can work on.
I have a
Okay.
question like
Actually, there's
from
a
the
question.
and
Yeah.
it says
Continue,
like,
Shay.
is there any particular platform you suggest for taking up extra courses like Python or Java?
Okay, so I personally I personally started from Andrew Ng's courses. So I would 100% suggest you to start with Andrew Ng's machine learning and deep learning courses. So those are free to take up, and gets you really well started with machine learning and deep learning. Apart of that, I wouldn't suggest any particular courses uh, for for a particular framework or so on. However, you can take a look. However, if you are interested in TensorFlow, you can take a look at uh, Lawrence Morani's course, which is really good. I had also given a try to it. And I also maintain a blog series which is called Deep Learning with TensorFlow. You'll find that on my Medium. So you can start by taking a look at both of these specifically for learning TensorFlow. But for starting with machine learning or for just taking up extra courses and not a particular platform, but rather I'd suggest you to take both of these courses.
Okay.
And with
So last
statistics,
question.
there's
Yeah.
a question in the YouTube.
Yeah. Go on.
Will statistics help us to learn AI/ML?
Oh, definitely. Definitely. You also do want to know about statistics. You definitely want to know about statistics. So, a lot of things in AI is based on probability. And let's say, so not in case of our algorithm, the algorithm which we built today was pretty basic and performing well. But a lot of things in machine learning are dependent on on probabilities and statistics. So you definitely do want to take a look at them.
Okay.
Oh,
So do you
Chandru
have
sir, do
any
you have any?
last end words to our listeners? What what would you say?
Oh,
If you have
sorry, I
any tips
couldn't
for
hear. I couldn't get you. Sorry, could you repeat again? I beg your
if
pardon.
anyone
Yeah.
wants to get into the field of AI/ML, if you have any tips for them?
Okay, so I would definitely suggest that Andrew Ng's two courses, which I mentioned earlier, because well, those got me started into machine learning. So I would definitely recommend those two courses. as a reading material. And I would also recommend the deep learning with TensorFlow series, which I run on Medium as a blog series. If you want to take a look at actually building machine learning algorithms, trying out simple machine learning algorithms, or building something with it, or more on the applied side of it, you would definitely want to take a look at the blog series which I maintain. So I would give these three. I'd give these three resources to help you get started, and there are a lot more, but these should very much help you get started in this field and give you good knowledge about it.
So there's one more question in the comments. Which programming languages are helpful for AI and ML?
Oh, so uh, that's so as of now, most of AI/ML stuff is done. um, Most of the model training is done in Python, but it's also dependent
Okay.
on which stage of AI/ML you are talking about. So let's say if I want to do an ETL job, uh, I would rather do it in SQL, but I want to actually train the model and gather some insights about my data. I would do that in Python, and if it's actually deploying my model, I would I would maybe have to do it in Node.js if I want my model to run it on the browser, or I could also do it in Python. And there are a lot of languages which are helpful. There are also new languages coming up. So if you so there can be an answer for which is the most used language, but there is no answer for which programming languages are helpful, because a lot of uh, you now also have TensorFlow Java allowing you to perform deep learning in Java and Kotlin. So it's a lot about, there are a lot of languages with which you can do, uh, but the basics with every language would essentially remain the same. I hope that makes sense.
Yeah.
Thank you for answering our
Vedant.
questions today.
Thank you, Rishit.
Thank you. Also, uh, if I haven't answered a question, I hope you understand that while I was taking up the talk, I couldn't follow along each and every comment. So really sorry if I might have missed your question while we talk. What you can do is feel free to send me a Twitter DM, and I'd love to take your question off stream too. If you come across any question after this talk while implementing it, feel free to message me, and I'd love to help you out.
Thank you.
Thank you. It was my pleasure, and thank you for inviting
Thank
me
you.
to TSU.
Hi, thank you, Rishit, for the amazing session. We'll be meeting you tomorrow at 7 a.m. in the morning, and the details will be shared to you soon in the groups. So thank you everyone for joining today's session. I will meet you tomorrow morning. Bye, guys. Bye.